Let's start. Right, so it's 4 o'clock. Welcome everybody. Good afternoon to our Thursday colloquium. But the number creeping up still. But let's start. We have been doing this for almost a year and a half now. It seems like eternity. And now, instead of every week, we have gone to every other week. Just to keep you on your toes. And so today, I'm very, very happy to have Chris Harrison from Newcastle University. He's a new ACT fellow, academic track fellow at the School of Mathematics, Statistics and Physics at Newcastle University. We know other people from Newcastle University too, and some of them would be on the participants list. Hi, Anwar. And so Chris did his PhD at Center for Cosmology at Durham University, and then has been a postdoc there, as well as has spent some time in ESO as a postdoctoral fellow, and is now at Newcastle University. And he works on the effect of AGN on host galaxies, on star formation, and all that kind of stuff. And very, very interesting to many of us here in NUCA and our associates. Over to you, Chris.
Great, thank you very much for that nice introduction. So yeah, today I'm going to talk to you about the multifaceted approach I try to take to understand AGN feedback, because I believe that you can't really understand this problem if you only take it from one perspective. So I really try to look at many different ways of approaching this problem, both from looking at individual objects, looking at statistical samples, and also more recently incorporating simulations. This work is led mostly, the most recent work is led by students. So the names in bold there are students that I've worked with, and I'll bring up their work one by one. And a lot of what I'll talk to you today also involves the Quasar Feedback Survey, which is a big team of people from across the world. So I'm aware that we have a range of expertise in this colloquium, and we have students too. So I thought it was important to give some broad overview first. So I'll spend the first 5 to 10 minutes giving the background before focusing on the work I've been doing. But before I get started, I want to tell you my take-home messages in case you drift off. So I'll spend the next 45 minutes or so trying to convince you of two main points. Low-power jets are common, and they're an important part of how supermassive black holes impact on the multi-phase interstellar medium inside their host galaxies. And the second thing I want to try and convince you is the importance of, if we really want to understand how AGN feedback works, we need specific model predictions that we can observationally test. I think we spent too long as observers testing vague ideas and getting ourselves lost. We need really specific things that we can go away and test. I'll try and convince you of these 2 points. So let's take a step back and ask, why are we interested in this at all in the first place? So we now know, we're very convinced that supermassive black holes reside inside all massive galaxies. Of course, the best evidence for this probably comes from our own Milky Way galaxy. And if you watch the stars over the last 25 years at the center of our Milky Way galaxy, they're orbiting some massive, compact, invisible object, which we now know must be a supermassive black hole, about 4 million solar masses. And this was the winner, this work, observational work, was the Nobel Prize winning work most recently in physics. And of course, we've seen recently too, the Event Horizon Telescope looking at the center of our nearby galaxy. And here we see this beautiful ring of emission that's perfectly consistent with there being a supermassive black hole. Fantastic work here using telescopes all over the Earth to make this image. So we're convinced that there are supermassive black holes in the center of massive galaxies. Now, how do you grow these supermassive black holes? Well, primarily through mass accretion. And when these black holes are growing, material spirals down onto the black hole, forms these accretion disks, and these emit emission across the whole electromagnetic spectrum. And if we detect this, we call it an active galactic nuclei. That's basically, if we can detect this emission from a growing black hole, we say it's an active galactic nuclei. And the energy that can be released is enormous. At their peak growth periods, they can outshine their entire host galaxies. And when we talk about AGN feedback, what we really mean is that this energy that's being released from the AGN is having an impact on the growth of the host galaxy in which it resides. And this energy could transport into the host galaxy through different forms. So we've got radiation, just the light, the photons from the accretion disk. We have winds that can be launched from the accretion disk region, and we have jets of charged particles, collimated structures that also come off these AGN. When it comes to radiation winds, it's quite simple that the amount of energy released in these forms is directly related to the mass accretion rate, or equivalently the luminosity of the AGN. While for jets, it's a little bit less clear, the connection between the mass accretion rate and the amount of power you get from these jets. And what I'm going to talk about is how jets can often be ignored or thought as subdominant in these radiatively powered systems. Well, actually, they may be very crucial. So a lot of energy is there, and this energy really, just from very simple sort of binding energy arguments, you've got enough energy to remove all of the gas from the host galaxy. But is it really needed in galaxy evolution? And the answer is yes. In our current understanding of galaxy evolution and in all simulations, this energy is required to have an impact in the host galaxies and effectively regulate the star formation. Otherwise, we can't produce realistic looking galaxies. So let me talk you through this with a sort of a toy model using some example simulations. So this is a plot of stellar mass divided by dark matter halo mass as a function of halo mass. So the more massive galaxies on the right, the lower mass galaxies on the left. And from empirical evidence, we know that there's this sort of curve here. Now you can think about this y-axis as the efficiency of baryons being converted into stars. If I have a certain supply of baryons, how efficiently can I convert them into stars? And we know there's a peak around just below 10 to the 12 in the halo mass, or equivalently about 10 to the 10 in stellar mass. That's where you get the most efficient growth. But it's less efficient at higher masses and also lower masses. If you make a model or a simulation with no feedback processes whatsoever, you end up over-predicting the amount of stellar mass across all masses, as demonstrated by this gray dashed curve. If you allow star formation to self-regulate, so if you've got supernova explosions, for example, this can churn up the gas, blow away gas, and this causes self-regulation, star formation feedback or supernova feedback, you're able to suppress the efficiency of star formation at lowest masses and get something a little bit more like what we see in the real universe. But it's only with the energy supply from active galactic nuclei are we able to get enough energy to suppress or regulate at least the star formation at the highest masses. And that's what you get on this black curve, and you've really pushed this down and you're starting to get a shape that looks like real galaxies. But it's not just getting the stellar masses right. Simulations incorporate this AGN feedback for a number of reasons to get realistic looking galaxies, including getting correct galaxy sizes, getting the right distribution of metals inside the intercluster medium, intergalactic medium, getting star formation rate distributions right. So a whole range of reasons that this AGN feedback seems to be important, at least inside these simulations. So how might you actually do this? Now, the cosmological simulations is very crude in how they can do this, but we also have a number of individual galaxy simulations where we might be able to resolve these processes a bit better. So I'm just going to give you a little snapshot of some examples just to sort of show you the variety of methods that people are exploring. So here's one example simulation. We're looking at a velocity map at several snapshots in time. The blue region across the center here, this cold gas, is a cold gas disk. It's a dense disk, supposed to be like a redshift 2 galaxy. And an AGN is put in the center with some simple thermal energy injection. So that releases energy, and the result is you get this outflow of material, which propagates through time here, this high velocity material above and below the disk. This is slightly preferential above the disk. But interestingly, the impact on this particular galaxy is very minimal. It has not any appreciable impact on the concurrent star formational properties of the disk. Now, what happens in the future, it's not clear, but very little happens to the disk in this simulation, despite this powerful outflow. Here's another example simulation. In this case, they incorporate a disk wind at the center of the interstellar medium. It's a complete interstellar medium. And again, this is a density map, but the details are not that important. Again, a large scale outflow over kiloparsec scales propagates, this time launched by a disk wind. And Ilverian Dipanjan also looks at this, particularly interested in jets. So I mentioned jets. Now, if this is an example from these simulations, again, a jet this time is the energy source hitting the could-be interstellar medium. The effect of this is to churn up material and cause this highly disturbed material and outflowing gas above and below the disk. And I briefly mentioned the cosmological simulations. Now, this is illustrious. This is one example, and they have two different modes of incorporating their feedback. They have what they call a kinetic mode and a thermal mode. And it's a little bit arbitrary, in my opinion, how they choose how to use these modes. So the point is there's this whole different array that AGN feedback might work. And the impact that they have on the host galaxy is very different, depending on many properties of how the simulations incorporate their feedback. So what we really want is observations to see what's going on in the real universe, and I'll show you what we're doing towards that. But let me give you a little bit of perspective of the parameter space I'm mostly interested in. So this is just a silly little schematic, really. There's jet power on the y-axis and radiative power on the x-axis. I will talk about quasars, which means I'm interested in these radiatively powerful systems. So there's a lot of energy being released as photons, and these winds may be very important. And there's another line here that defines radio loud and radio quiet. Now, this is a traditional definition, and in a very crude sense, you might think things above this line are jet dominated, and things below this line radiation or wind dominated, in a very crude way of thinking about this. And then there's this area of parameter space then that we have, which we call radio quiet quasars. So sort of naive traditional idea might be for radio quiet quasars, the most important energy injection mechanism is either just directly from radiation or from these accretion disk winds. And so I'll talk to you about our study of these radio quiet quasars. In terms of the observations I'm making, well, this feedback happens over orders of magnitudes of scales. So I'm showing you another schematic here where we talk about temperature on the y-axis and logarithmic distance on the x-axis, all the way thinking about the torus and the broadline region and these accretion disk winds through to the interstellar medium, circumgalactic medium, and beyond. Feedback is sort of explored on all of these scales. And we should bear in mind that that results in a huge range in timescales. So this is something that's very important for understanding the observations, because we can't track individual objects. We have to really bear in mind the huge timescales involved from the scales of the AGN to the scales of the host galaxy and beyond. So while people are studying feedback on the large scales, particularly, for example, looking at jets and how they interact with the intergalactic medium or the intercluster medium, and people study the disk winds at small scales, my focus will be on the interstellar medium and looking at the multi-phase gas all the way from hot phases down to cold phases, and see if we can see how these AGN are interacting with the interstellar medium inside the galaxies that they reside. So what kind of approaches can you take to do this? Well, spectroscopy is one of my favorite approaches, and looking at emission or absorption lines to measure the multi-phase kinematic properties. So starting with the warm ionized gas, so I mean 10 to the 4 Kelvin sort of gas, the common line to use is the emission lines in the nebula lines in the optical. So for example, O3. Here is an example emission line profile that looks very symmetrical, and maybe this gas in this galaxy is doing something very boring, sort of galaxy dynamics. But we're often looking for these broad underlying components, which can reach 1,000 kilometers per second. And this can be a tracer that there's outflow material, or at least turbulent material inside. So I'll be using this oxygen 3 line. People have also detected outflow material in neutral and atomic phases. So again, you sort of see different components, this time in absorption, something at the systemic of the host galaxy, but then wings out to higher velocities, implying outflowing material. In this case, you'll be traveling towards you. And again, a similar thing seen in H1. This was a sodium D line. Also, people have seen this in the warm molecular gas. So this is sort of hundreds of Kelvin type regime. And also in the cold molecular gas, again, we're seeing this underlying component. Now we're in the sort of 10 Kelvin regime. And for this, carbon monoxide is one of the favorite tracers to do. So I'll particularly, my work, I'll be using CO and O3. The kind of questions I want to ask using these observations are, What are the multi-phase outflow properties? So for example, what's the energy and mass involved in these flows and what drives them? So I kept going on about what's the most important energy injection mechanism. Is it jets? Is it winds? And the second question that I'll touch upon today is there observational evidence that quasars are having a direct impact on their host galaxies? And can we see what we sort of expected to see from the simulations, that there is an impact from these AGN on the star formation, or at least the gas properties of the galaxies in which they reside? Okay. So having given you the background and the motivation, I'll move on to our work. So I'll start with this first question I've posed. What are the multi-phase properties and what drives these outflows? So as I already mentioned, I'm going to particularly focus on this oxygen 3 line. So this is tracing the warm ionized gases, just a reminder of this emission line profile that we often fit in 2 components, a broad component and a narrow component. And this is fairly historic work, but it sort of sets the scene for what we'll see next. Is we took a sample of 24,000 AGN host galaxies at redshift less than 0.4, and we explored what is the prevalence of these high velocity features, or importantly, what is driving the prevalence? What's the most important property of the AGN or the host galaxy that determines how prevalent these outflow features are? So back in this Mullany 2013 paper, there's lots of information there, but I want to just give you the highlight result, and that's the importance of the radio emission. I'm showing you here a cumulative distribution. So this is cumulative fraction on the y-axis, and 4½ max is the average velocity width of these 2 components. But really, you can just think about this as how extreme is the ionized gas velocities in the host galaxy. So by the time you reach 1500, 2000, you know you're in a very extreme regime. Something must be going on here that's beyond galaxy dynamics. And we split this into various different subsamples, and what we found was the most important parameter was the radio luminosity. So this black curve here is the full sample. And if we split this by radio luminosity, around 10 to the 23 watts per hertz, at lower radio luminosities, you get this blue curve. So these high velocity features are much less prevalent compared to if you look at the higher radio luminosity systems determined by this red curve. So by the time now at 1500 kilometers per second, you see these are much more prevalent in the moderate to high radio luminosity systems compared to the low radio luminosity systems. And I've used the word moderate because 10 to 23, we're not talking about extreme radio loud systems. In fact, this sample is dominated by traditional radio quiet. It's just at the more moderate regime in radio luminosities. So something interesting is going on in the radio, but this one-dimensional study doesn't give you too much more information than that. So this led me to try and push this a little bit further, and this was work led by a student. He's now a PhD student, Stephen Molyneux. He's at ESO as well as Liverpool. And we took a subset of that sample, 3,000, which had detections in either the FIRST or the MVSS radio surveys. And we focused on redshift less than 0.2 because that means we could do a little bit more detail. And what we wanted to ask was, could we see a connection between how compact the radio emission was and the prevalence of these radio features? So using a combination of machine learning techniques, direct measurements on the FIRST data, and also follow-up studies to sort of check that our size measurements were reliable, we split the sample into compact and extended sources in terms of the radio. So here's some compact examples. The first image is in the background, and then there's some radio contours on top. Here's some examples of some high resolution follow-up. We didn't follow up all of them, but just a subset to make sure things look reliable. And in these cases, the radio emission is fairly compact, which means about less than 5 kiloparsecs. And then here's some examples from the extended subsample. In the background, you see the radio emission is much more extended and even beyond the fiber of SDSS. And then this is the same plot as before, a cumulative fraction against 4½ max. And we can see that the extended sample, you have much less prevalence of these high velocity features compared to these compact systems. Now, again, we can't say for sure what's going on, but our suggestion was that if we have compact radio emission within inside the host galaxy, maybe radio jets, these are having a high impact on the host galaxies, causing these high velocity features. Or maybe if the radio emission is extended beyond these extents, we're not seeing that impact on interstellar medium. So taking that a step further now, going in, so we started with this big sample, we focused on a slightly smaller sample to do a bit more, and now we want to go super detailed on another subsample. So this is the basis of the Quasar Feedback Survey. So we're now taking 42 of those objects, and we want to study them in exquisite detail to really understand what is going on inside those systems. So these are 42 quasars, redshift less than 0.2, volumetrically luminous, so greater than 10 to the 45 in volumetric luminosity. And this corresponds to the knee of the luminosity function at redshift 1 to 2. So although they're actually quite rare in the local universe, these are typical of the luminosities you see in the higher redshift universe, where AGN activity is generally more prevalent. And we're slowly building up this multi-wavelength survey of these 42 objects. We already have extensive radio data from VLA and eMerlin for the full sample and GMRT. And we're slowly building up the other multi-wavelength data from all of these facilities to understand the multi-phase gas kinematics. And I'll show you some of the results of this. And this builds upon some pilot studies we did over the last few years before we ended up with this main survey, and there's some references to this. So just to understand the sample selection a little bit more, in the background, I'm showing you the Mullany 2013 sample, this parent sample that I was talking about. These are the green contours and the green data points. And on each of these panels, the stars are the 42 objects from the Quasar Feedback Survey. On the x-axis here, on the y-axis here, we have the full width half max of the O3 line. So how broad is that O3 line? And the important thing about our study is we no longer want to focus only on extreme systems, but we're sampling the full range of ionized gas kinematics from the parent sample. And then this dashed line shows you the O3 luminosity threshold for which we're creaming off these most powerful systems. So O3 luminosity is a nice proxy for bolometric luminosity, how much radiative output or what is the accretion rate of the AGN at the center. Then in the right panel, I'm showing you radioluminosity versus O3 luminosity. So this goes back to that schematic I showed at the beginning. Things above this line are radio loud, traditionally thought of being jet dominated, and things below this line are radio quiet, so where jets traditionally think subdominant. And we have a weak radioluminosity criteria, but you can see that nearly all of our sample, just a handful exception, are in this radio quiet regime. So I'm studying these radio quiet quasars predominantly, which I've mentioned there. Now, some of the work that I'll present is only on our pilot sample. So I've circled those here, these 9 objects. So I'll try to keep track of when we're focusing only on this pilot sample versus the full sample, but over time, we're building up this multi-wavelength data for all targets. So here's a little snapshot of examples of some of the VLA radio data we have. So we went this to 0.3 arcseconds resolution. So this gives you about a kiloparsec scale or better spatial resolution, but we also imaged at different resolutions so we could try and measure both compact structures all the way to diffuse larger objects. So there's just this little montage of the kind of radiomorphologies we're seeing. And you're seeing a high prevalence of these collimated radio structures, as well as things that look more like radio lobes, extending only from a couple of kiloparsecs all the way up to 60 kiloparsecs. And the important thing is most of these interesting radio structures are not resolvable by all-sky surveys currently, such as FIRST and MVSS. So you really have to push the radio data if you want to see these interesting structures. So you kind of split the sample into things that show extended, that show X radio structures and things that don't. We found that 2/3 of the sample show clear radio structures in our radio imaging, often looking like these collimated radio structures that one may associate with jets. Now, I don't want to go into all of the details today, but you can look at Miranda Jarvis's 2021 paper. And we took the sample and we looked at many different methods to ask what's producing the radio emission. So on top of morphology, we also looked at, is there more radio emission than we expect given their star formation rates? What's the spectral index and the surface brightness temperatures of the radio cores? In order to understand, is it AGN that's dominating the radio emission or star formation? And what we found was at least 57% of the sample are AGN dominated. For the rest of the sample, we didn't have sufficient data to determine if it was AGN or star formation dominated. So it's a lower limit, at least 57%, this radio emission is AGN dominated. And so that's 24 in numbers, and that compares to only between 3 or 9, depending on your favorite definition, being classified as radio loud, defined based on previous sort of typical approaches. So there's various common approaches in the literature to screen off radio loud objects and radio quiet. Most of ours wouldn't fulfill those, but if you dig deeper into the data, you see that radio AGN are extremely common, even inside these so-called radio quiet quasars. So the message here is radio emission is important. We shouldn't crudely just forget about it, even if they're traditionally classed as radio quiet. So thinking about that now, what can we see if we look at the multi-phase gas properties of the interstellar medium? We've identified these radio structures. How do these relate to what we see in the gas properties of the host galaxies? So this work is on that pilot sample I mentioned. So it's 10 objects in total in this case. All of them are radio quiet. And I'm going to show you some integral field spectroscopy that allows us to map the ionized gas compared to the radio structures that I saw that come from VLA and HEMO. So here's a little montage of those. In the background, the maps are showing you the distribution of the O3 emission, the ionized gas, where darker colors are brighter. And on top, I'm showing you contours of radio emission from various different types of radio images. So there's green contours, which are low resolution, blue contours, which are high resolution. But if you look carefully, you can see again these collimated jet-like structures in many of the objects, as well as these radio lobes. And what you see quite clearly is there's a spatial correlation between these jet-like structures and the ionized gas. So instantly indicates there's some interaction going on between the ionized gas and the jets, or maybe these jets are even boosting the ionized gas that we're seeing. So you can sort of see something going on here. There's clearly some correlation going on here between the end of this jet structure and this jet structure with the ionized gas. This is very common across the sample, but we don't just have spatial distribution information, we also have velocity information. And again, we find there's a very strong relationship between the velocity structure and the radio structures. So for example, zooming in on this object, you're seeing a velocity map now in the background, blue to redshift, nicely aligned with this radio structure. Another example, very similar again, radio structure is aligned with the velocity structure. And here, this is a nice signature of potentially a bent jet, potentially colliding with a gas cloud here and giving it some sort of velocity kick. So we're seeing signatures of jets interacting with the interstellar medium commonly across this sample. Now that was work done back in 2019 with a student, Miranda Jarvis, using VMOS and GMOS data. Now we have MUSE data for 18 of the objects. Now, for those of you who don't know, MUSE is this fantastic new integral field spectrograph. The quality is nothing like been seen before. So the spatial resolution's increased, the sensitivity's increased. So we have a huge amount of rich information inside these data cubes for these objects. And so this is work being led by Aishwarya Girdhar as part of her PhD thesis. I'm just going to show you one example object and give you a little taster of the kind of things we can do with these MUSE data. So I'm showing you this one galaxy here. This is a continuum image, looks like a spiral galaxy. And these data we have allow us to map not just the gas kinematics this time, but also the stellar kinematics because of the sensitivity of the data. So this panel here is showing you the stellar velocity, and it looks like the basic signatures of a rotating disk. The panel on the left is the ionized gas kinematics. Now, if you look at this sort of just crudely, it looks like the gas is broadly following what the stellar emission is doing, the stellar kinematics. However, if you make a residual and you compare the ionized gas to the stellar, you see that something is going on that doesn't look like the general galaxy dynamics in the gas in the central regions, in particular perpendicular to this radio jet, which is shown as the contours. So we're starting to see some non-gravitational motion signatures around this jet region, as I just mentioned. So let's zoom in more detail on that central region. So the maps I'm going to show you now are just a zoom in of this sort of central nuclear region. This is a velocity dispersion map of this central region. The contours again show you the jet. This is the ionized gas. And what we see are these remarkable cones of extremely high velocity dispersion gas propagating perpendicular to this radio jet, reaching values of well over 1,000 kilometers per second. And we don't just have integral field spectroscopy to map the ionized gas. We also have ALMA data, which, going back to the earlier slides, using carbon monoxide, we can map the molecular gas, the cold molecular gas. And I'll just show you one little plot from that. We see a similar signature just above the jet of high dispersion gas in the molecular cold phase, although it's much less extreme in velocity, so only more like 600, 500 in this case, and it's not as extended as we see in the warm ionized phase. We're putting this in a very crude schematic. What we think we have is a rotating galaxy disk. We think we have a jet that's pretty much in the plane of the host galaxy. I haven't shown you all of the data because there's too much to show, but we've got some interaction points at the ends of the jets. But we think pluming above and below the galaxy disk, because of an interaction, we're seeing this highly turbulent outflowing material. And this is qualitatively similar, at least, to what we're seeing in simulations that I showed at the beginning, thanks to Dipanjan. And Dipanjan's part of our team, and we're having ongoing conversations about how we can relate what we're seeing in the data to the predictions of the simulations, bearing in mind parameters such as jet power, inclination angle, etc. So that's all work that we're working on right now. So putting this one object in context, of course, we have the rest of the sample to be analyzed, and that will come. But this is particularly interesting because going back to this idea of the importance of radio jets versus quasar winds and radiation, if we plot objects that are similar things have been seen in the literature, that's shown by these blue points. So this sort of high velocity dispersion gas going away from these jets, this has been seen before, but mostly the ones that have been studied are in these low radiative power regime. So it's indicated here, these sort of what we call the Seifert regime. We're now pushing into the quasar regime, where jets have been traditionally thought subdominant, but we're seeing the same effect. So maybe even in this quasar regime, jets can be potentially the dominant mechanism for causing these outflows and turbulence. Of course, we've only got one object for now, but as time goes on, we'll see what we see across the wider sample. So that brings me back to my first take-home message that I wanted you to take away. We're seeing that low-power radio jets are common across these quasar systems, and they appear to be an important mechanism for how these AGN are interacting with the interstellar medium of their host galaxies. Okay, so now I'll move on to question 2 that I posed at the beginning of my talk. Is there observational evidence that quasars have an impact on their host galaxies? So we went back to this idea that simulations, the model saying they must. We're seeing these outflows, sure, but can we see direct evidence that they're actually having an appreciable impact on the evolution of the host galaxies? And this has sort of been a bit of a holy grail for observers over the last decade or so. However, I would argue that we've been floundering around not really knowing what we're looking for. But let me present sort of a couple of approaches, and then we'll discuss if that's the right approach and how we might move forward. So going back to this Quasar Feedback Survey and these objects that I showed you, where we clearly see these jets and this interaction with the ISM, we went and got measurements of the carbon monoxide to get total gas mass estimates of the host galaxy. So this was done with APEX. Here's some emission lines. You can just sort of see the data there. And the question we posed was, do they have depleted molecular gas reservoirs? Maybe that's what you'd expect to see if this AGN feedback is having an appreciable impact on the host galaxy. And the answer is no, they did not. So here's a couple of plots to show this. This is the CO luminosity, but we can think about this as a molecular gas mass. And then this is fine infrared luminosity, but we can think about this as star formation rate. Our data points are shown here. As the circles, this gray band is typical star-forming galaxies, and this dashed line is what we call starburst galaxies. So these things have a lot of star formation rate for their stellar mass. We've color-coded by how starbursty our systems are. So things that are yellow are starburst, and things that are purple and blue are star-forming. And what we find is, based on their star formation properties, these AGN with these jets and outflows just fall exactly where you'd expect for any other star-forming galaxy or starburst galaxy. To put this in another set of plots, here we have gas fraction, so that's molecular gas divided by stellar mass as a function of specific star formation rate, so that's star formation rate normalized by stellar mass. In the background, you're seeing normal star-forming galaxies where we don't see the AGN, some low-power AGN shown as squares, and our extreme high-power quasars with these outflows as black data points. Everything falls on the same relationship in all of these planes. So based on this approach, we don't see any depletion in the molecular gas reservoirs or any impact on the star formation rate efficiency. Now that's just for that pilot sample that I've been talking about. We have a wider survey going on led by Stephen Molyneux again to see what we see across that sample. But I want to ask the question is this observation, and I have some other ways of approaching this if we have time, inconsistent with this idea that AGN are blowing away gas, preventing star formation? Are they depleting their gas reservoirs? So bringing back this sort of motivation at the beginning. And many papers in the literature have seen similar things to what we saw. I put some references up there and said, AGN live in gas-rich galaxies, therefore feedback isn't happening. But I wasn't sure that this is the end of the story and things aren't that bad. I said, well, we haven't actually tested a particular prediction. We've just tested some vague, broad idea. And when people have looked at star formation rates, they've come to similar conclusions. Oh, they're star forming, therefore no feedback. But these are just broad ideas. They're not actually specific predictions. So what we wanted to do was go to some of these famous cosmological simulations and say, well, what do they actually predict? If I try to emulate broadly what I'm doing in the observations, what would be the prediction from the simulations? So here's just a nice picture from Illustris TNG. These are large volumes of the universe, so you have thousands of galaxies to work with, including AGN. They all have this feedback processes. So feedback's crucial, but what do they actually predict for these type of observations? And this is work being led by Samuel Ward. He's a shared student of mine across ESO and Newcastle, as well as MPA actually. And we're asking that question. Do these sort of observations, which we find AGN live in gas-rich star-forming galaxies, rule out AGN feedback? So we're taking 3 of the most famous hydrodynamic cosmological simulations, Illustris TNG, Eagle, and SIMBA. They all have roughly the same box size, so it gives you a nice large sample of galaxies to work with. And we've taken the H2 modeling that's been developed by these teams, so it's well tested and well established. Yes, it's post-processed, but it's been well shown to sort of globally reproduce galaxy properties. And they all have slightly different ways of implementing their AGN feedback, either thermally or kinetic or some sort of combination of both. So just taking the simulations, taking the outputs from these simulations and asking what do they predict. So this is a gas fraction versus stellar mass plane. And it's these density plots, and it's color coded by the luminosity of the black holes. It's really accretion rate, but we've converted it into volumetric luminosity. So yellow colors are representative of high accretion rate luminous AGN, and darker colors are representative of low accretion rate, low luminosity AGN. And you can see typically the yellow colors are in the higher gas fraction regime. And this is plotted as a one-dimensional histogram on the right. If we take some sort of cut to define AGN, it doesn't matter how you do it, you get the same answer. AGN live in gas-rich galaxies, as predicted by this one particular simulation. This is Illustris TNG. AGN live in the gas-rich galaxies. But if you look across the sample, across the 3 simulations, so I've got on the top row TNG, then Eagle, then SIMBA, and on the left, it's star formation rate, mass normalized, and on the right, it's molecular gas fraction. We get pretty much a consistent picture that AGN are predicted to live in gas-rich star-forming galaxies. So despite this feedback process, it doesn't instantly mean that you should see an appreciable depletion of gas or depleted star formation rates in galaxies that host the most powerful AGN, as predicted by these very specific set of simulations. But the point is, observers have often made these very basic plots and said, we don't think feedback's there because AGN live in gas-rich star-forming galaxies. And the point we want to make here is, well, the simulations don't even predict that. However, there's more to be done here because there are subtle differences between the predictions and simulations. And then it starts to get interesting because they all implement feedback in a slightly different way. So we can start to ask which one of these is more realistic. So I'm showing molecular gas fraction against volumetric luminosity or black hole accretion rate. for Eagle, TNG Simba, and some observations here. Now, this blue shaded region are these sort of quasar regime or high luminosity regime, and below this dashed line is things that you might call quenched. Now, fortunately, there's not a lot of overlap between the observations and the simulations due to volume issues. We can discuss why that's a problem. But I just wanted to highlight the differences between TNG 100 and Simba. They have similar ways to implement their feedback, but they have very different predictions for where their quenched populations live in this plane. In TNG 100, they're mostly in this very low accretion rate regime, while there's a tail, a little small tail into the high accretion rate regime of these quenched galaxies in Simba. So I think there's more work for us to be doing here in understanding how realistic these different feedback prescriptions are, and we can start actually testing them directly with observations, specific predictions, rather than just some vague ideas that's sort of been the approach over the last few years. So just to sort of summarize a little bit what's going on here, AGN feedback is clearly crucial in the cosmological simulations to regulate star formation, but they do not predict that luminous AGN typically reside in quenched galaxies. Even though I would say most observational papers I read haven't sort of made that important connection. Now, what might be going on here? Well, one sort of obvious explanation is the feedback process happens over longer timescales. So it's not an instantaneous process. You don't just suddenly blow up the galaxy. You can gradually inject this energy over time, and that makes it more difficult for gas to collapse onto the host galaxy and to form stars. So that would be one way to sort of explain this fact that we've seen in the observations. There's also the possibility that lower power systems could be the most important for the feedback. So it might not be, you should focus on these high accretion rate systems. Maybe these lower power systems are more important, and there were some signatures of that maybe in TNG 100, but I think we need to do more to understand which systems we think are the most important. And the message I want to get across from this is we really do need specific tests of different ways feedback might work, so we can go to the real universe and test them. So I've got a little bit more time, so I'm just going to show you one more result before I give my summary, if that's okay.
Yes, please, go ahead.
Yeah, so it's a sort of similar line, but I'm going to have a little bit of a shift. I'm going to work to the high redshift universe. And it's a similar thing, asking, do we see an observational signature that star formation has been suppressed by these AGNs, specifically these outflows? So as well as this low redshift work, I also work at high redshift, and again, using integral field spectroscopy to map ionized gas properties. And there was a series of papers a few years ago saying that they'd seen direct evidence for suppression of star formation by these ionized outflows. So what they did was they used H-alpha emission to try and map the star forming regions, the regions of star formation. And they used the oxygen 3 line, the high velocity wings of the oxygen 3 line, to try and map these ionized outflows. So these are from these papers here, but these are the 4 famous examples where the background map shows you H-alpha emission, which they suggest is tracing star formation. I wouldn't agree, but that's the claim here. And the contours are showing you the location of the ionized outflows, the high velocity gas. And there appears to be a cavity in this interpretation of the star formation at the location of the ionized outflows. Now, going back to what I was saying before, it's not clear to me that that's even what's predicted in the simulations. I showed you one right at the beginning where the outflow didn't actually have any impact on the disk, and maybe we don't expect to see such a rapid impact, but this is apparently what we're seeing in the observations. But I was a bit dubious, so working with Jan Scholz as a student who was at Durham and then spent time with me at ESO, we went and got ALMA data to map the dusty star formation inside these galaxies, and re-looked at the IFU data. And this is just an example of what happens if you compare dust distribution. So this is the red contours with the H-alpha emission. And you often see this offset. On face value, this could simply be that the dust is obscuring the H-alpha emission. So you ought to be very careful about using H-alpha emission because of dust obscuration. But furthermore, when we kind of used different tracers to look at the star formation, we used the dust emission to trace star formation as well as the H-alpha emission, we were not finding any of these cavities. So The maps in the background is showing H alpha emission, the red contours of the dusty star formation, and the white contours of the outflow. We weren't seeing in our sample any signatures of these cavities caused by these outflows. And even when we went back and looked at the same object, so this is one of the specific objects that I mentioned before from the literature. This is the same object reanalyzed by us, H alpha in the background, dusty emission here, and outflow here. So we get the same sort of output for the outflow, but we have a different interpretation for the star formation, and we didn't detect these outflows. And in Jan's latest paper in 2021, we also went and looked at those quasars, all four of those objects that I showed you, and we come to the same conclusion. So we are not seeing evidence for this rapid in situ shutdown of star formation inside the host galaxies. But for me, that doesn't rule out feedback, because we don't even necessarily know if that's a direct prediction of these cutting edge simulations. So I'd really like to see more direct predictions of how these outflows impact on star formation, or what timescales, or what spatial scales, and then we can design observational tests to go and test. Okay, so I'll bring up my final slide. These two take-home messages that I wanted to give to you. So low power jets are common, and they're important for AGN to interact with the multi-phase interstellar medium. We shouldn't rule out jets even in these volumetrically luminous systems. And if we really want to understand how AGN feedback works in galaxy evolution, we need specific and observationally testable predictions from these different ways of prescribing feedback in these models. And I'd say recently we've just been testing the broad idea that AGN shut down star formation or remove gas, but it's probably more complicated than that. So we need specific predictions to test on these observations. And the last thing I'll say is I will soon be hiring 3 PDRAs in the next over the winter period, probably, including a simulator and a couple of observers. So if you're interested, I'll be very happy to hear from you. And with that, I'll stop, and I'm very happy to take questions.
Thank you very much. That was a very, very interesting talk, Chris. Thank you. Let's see whether I'm asking everybody who wants to ask questions to use the hands up option in the reactions category. I'll wait for people to put up their hand. I'll unmute them. So while we're waiting, Chris, can I ask you one quick question?
Yeah.
You talked about the difference in timescales from, yes. And so how is this difference in timescale actually handled in the various simulations you're talking about? The simulation, does it take some parameter that the timescale is dependent on?
Okay, so there's two. I guess it's.
I'm asking you for. I'll tell you what the context is, because there are systems in which you see star formation coexisting with evidence of AGN feedback, and so clearly there is a time scale mismatch between the quenching of star formation in the center of a very near where the feedback is happening, and stuff like that. So in a simulation, how would that look?
Well, I mean, the nice thing in the simulation is you can watch time, right? So for an individual galaxy, you can launch your AGN wind, or you can launch your jet, and then that propagates at whatever speed it's propagating on, and then you can see at what time it has an impact on the star formation. So you can plot star formation rate as a function of time, AGN accretion rate as a function of time. And often I think that there is a delay, because it takes time to heat the gas to cause that impact. And so by the time the star formation has an impact, your AGN could have switched off. So you may no longer have a bolometrically luminous AGN at the center of your galaxy by the time that process has managed to have an impact. Now, it's different simulations have different predictions. I know some of Tiago Costa's, they predict quite an instant impact in the very nuclear regions, for example, in the sort of in a kiloparsec. But to have an impact on the larger scales, that takes a lot longer time. So this is what I mean. You kind of need something specific to test, because if I'm looking at volumetrically luminous AGN, they might not be the right ones to look at to see if the quench systems, for example.
Right. So you're saying that the physics that's put in for the feedback itself has a timescale built in. It's not that the prescription gives a timescale dependent or timescale dependent on certain parameters.
No, I think it's the prescription that's put in will give you a time scale.
itself.
Because, yeah, so you inject a wind at the accretion disk and then you just watch to see what happens and how long it takes, for example.
Great. Dipanjan has his hand up. Dipanjan, go ahead.
Hi, Chris.
Hi.
Very nice talks, as usual. I'm very curious about the last part of the last results regarding this thing in not finding these cavities. Now, this is very interesting because this has been a prediction from the simulations as well, that you clear out the central region. So that the Gabor and Barnard simulation I'm talking about, they you see the edge-on image, but if you see the face-on, or even the Volker-Geibler simulations, you'd find there's a prediction for a growing central cavity where the outflows grow. It of course depends on the orientation and things like that. But what I'm wondering about is, first of all, where do these galaxies lie in the Kennigan-Schmidt plot? So it may not be that the gas is being stripped out, and that's why you get quenching, but it could be turbulence being injected into the system. Yeah. As we've seen in a few cases, for example, NGC 1266 by the KT Elatello group and others.
Yeah.
And secondly, what kind of outflows are these? Are these radio-driven outflows, or are these agent winds?
Yeah. Okay. So a lot of things to unpack there. So we should caveat this is high redshift, relatively low, so low spatial resolution observations, right? So the spatial resolution is normally about 4 kiloparsecs. So there's already a challenge there to deal with. The outflows are warm ionized outflows. So O3 trace outflows. We don't know about the role of the radio because the data isn't good enough to look. If this, for example, a tiny radio jet, we wouldn't be able to tell in these systems. They're star-forming galaxies. We don't have molecular gas mass measurements for these, so I can't tell you exactly where they are on the Kennigan-Schmidt relation, but they are star-forming galaxies, so they're probably gas-rich, but I don't know. But one thing you should point out that maybe wasn't clear is this is supposed to be mapping star formation, not gas. So that's the idea of the approach that they took. So going back to that Gabor simulation, even if the gas is depleted, I don't think there's an instantaneous impact on the star formation, right? So it's not that you instantly have a hole in star formation.
That's right. Now, I think it'll be very cool if you can get some data on the CO or to estimate the gas mass distribution to see where it sits on the Kennigan-Schmidt.
Yeah.
See if there's because what the Gabor simulation tells us is that the gas star formation in the large scale disk is not really affected too much.
Yeah.
However, I must give a caution here because there's a strong dependence on the momentum of the outflow. And if you look at this comparison between jets and winds by Salvo Cielo and their group, where they compared wind-driven outflows and jet-driven outflows, the momentum from the winds was not sufficient to do anything, any damage at all.
Yeah.
And so so that's an explanation maybe that you will not see a cavity in the first place, or if it's very small, then this large scale poor resolution would not really resolve those.
Yeah, I think so. I think a more, as you were alluding to, a more promising approach would be, rather than trying to map star formation, to map the molecular gas properties.
Right.
So look at the distribution of the gas. Is it turbulent? And also use multiple transitions in CO, for example, because it might be in a highly excited state. And I think that we can do at low redshift. And there are a few people working on that. And there's signs coming out that there is an impact on the molecular gas, like you were sort of alluding to there.
Right. Thanks, Chris.
Thank you very much. Anybody else? Any other hands up? Anybody else have any other questions? If not, going. Yes. Oh, yes. Forgot. Kandu, I forgot you. Kandu, go ahead. Yeah.
Very interesting 2 conclusions that you had, and left me quite confused.
I know.
Because on the one hand, you were showing various simulations which said that you have lots of gas even when the AGN was around or something. So this is not a signature of quenching.
Yeah.
On the other hand, you also had, you do get quenching in these simulations, in the sense that the stellar mass does finally explain the fact that you have a change luminosity function at high mass n.
Yes.
So there must be an integrated effect going on, or what's happening?
Yes, yeah, exactly. Yeah, I think that might be more the interesting quantity. So the point here is if you're picking out the actively accreting black holes in the simulations, they live in gas-rich galaxies. And it makes sense because you need gas to grow the black hole as well as to have star formation. So probably, as you just said, the actual quenching happens from an integrated effect over time of these sort of potentially these AGN episodes, and it might happen over a longer period of time. So if you're looking at an AGN, probably it'll live in a gas-rich galaxy, but over time, as that black hole mass grows, you might see a quench system. And in fact, if you look at black hole mass, the things with the highest black hole mass have had the largest integrated energy injection, and they typically live in more quench galaxies. So, but it's trying to connect all of these things and because feedback is implemented in many different ways in the simulations, I want to know which is right and which is more realistic. And so in terms of understanding these different populations, and on this slide, I showed you there was a difference in the prediction. I'm interested to go and test those to see, is TNG more like the real universe or is SIMBA more like the real universe?
So what was the difference in SIMBA? I mean, they did something different feedback?
It's the way, I can't remember, how Samuel will say, he's looked at this in a lot of detail. It's how and when they switch modes. So on face value, they both have a kinetic mode, which is you just give a velocity kick to the nearby particles, and a thermal mode, which means you just dump thermal energy around the black hole. But they pull in these different modes in different types of systems. So they all have a decision to make about when one mode kicks in and one mode turns off. I think TNG, you're either in one mode or in the other mode, while in SIMBA, you can be in both modes at the same time. So there's one difference that they do in how they implement it.
Oh, great. Thanks a lot. Thanks a lot, Chris.
Thanks very much. If there are no other questions, I suppose, thank you very much. It was a great talk.
Thank you for having me.
However, we can applaud the talk. Thanks very much, Chris. And again, please, we'd like you to visit us some point when things are possible.
Yes.
There are a lot of people here who are interested in this kind of work and in simulations in general in the cosmological context. So it'd be great to have you here. But it was a great talk, and let's hope we follow it up. Yeah, Anwar has his finger up.
Hopefully see you soon.
Okay, see you then. Bye.
Bye.
Bye. Thank you very much, Chris.